to uh, invite the presentation of the morning session, and the first who will present her work is Lindsey Corson from the University of Strathclyde, and the title of her presentation is Liquid Dielectrophoresis and Wrinkling on the Surface of the Fluid Layer.
Thank you very much. So I am currently a postdoc. I'm in the first year of a postdoc position up at the University of Strathclyde in Glasgow, working with Professor Stephen Wilson, who is in fact currently giving a talk over in the Gatehouse at the moment. So I'm very glad you're all here and not over there listening to him. And also with Nigel Mottram, who I'm sure a lot of you will know because he's been down here for the first 3 months of this year, and Brian Duffy. I should maybe start with not an apology, but I'm afraid the words liquid crystal are not going to appear anywhere in this talk until I get to the summary slide. So at the moment this work is very much on isotropic fluids, liquid dielectrophoresis, with the aim of then eventually expanding it to be anisotropic dielectrophoresis within a pneumatic liquid crystal layer. But today I'm just going to be presenting the work that I've been doing with an isotropic fluid. So there's been this growing technologically driven interest in using external forces to try and shape and manipulate small quantities of liquids in a process that's been called microfluidic actuation. And it's got lots of uses with lab on a chip and making liquid lenses and other things. And we like to use electrical forces to do this manipulation because then the devices that we create don't need to contain any small moving parts. And there are two existing techniques that we've got that are driven by the application of a voltage: electrowetting and dielectrophoresis. And I'm just going to take a little minute to give you some kind of pros and cons and some differences of the two. So with electrowetting, that's over on this side here, your fluid has to be conducting. And what we've got a grounded electrode on the bottom. We put a thin insulating layer, usually a dielectric, on top of that. You set your drop on the top, and then you stick your electrodes on top of your drop so you can get an electric field that then goes across your conducting droplet. And the moment you apply some kind of electric potential to this drop, the drop will spread, and that's why it's called electrospreading as well. With dielectrophoresis, however, over here, it doesn't need to be a conducting fluid. With a dielectric fluid, it's insulating, and the fluid doesn't need to remain in contact with both electrodes. So what happens with dielectrophoresis is that the particles inside, when you apply an electric field, the particles polarize, and then they want to move to the regions with the highest gradient in the electric field. And what you get in the liquid is you get a bulk force that then, as bits of the fluid then move to where there's the highest gradient in the electric field. So this problem that I'm working on has been motivated by some experiments done with the group that we're working with at Nottingham Trent, Carl Brown and Kostas Sinoskis. So what they've done is here we've got a droplet of propylene glycol that's sitting on a horizontal electrode, the dashed line, with another horizontal electrode about 200 microns above that. They apply an electric field, and the drop grows in height. It shrinks at the middle, grows in height, and the contact lines remain pinned.
Are you talking about DC or AC?
DC electric field. And then when you increase your voltage still further, at some point you get this very sudden formation of a capillary bridge. The contact lines deepen, and the drop then grows and hits the top plate. And this is a stable state for this drop. As you then decrease your voltage, it will sit quite happily as a capillary bridge. So it's the surface stresses at the liquid-air and liquid-liquid interface that drive the physics of this. And so what I'm going to be talking about today is a very simple 2D model of a horizontal layer of dielectric fluid subject to an initially vertical electric field. And just for some background, this work extends a model from Dimitrios Papageorgiou down at Imperial College, who has done a very similar mathematical analysis, but with an infinite electric field. So he doesn't have a top plate. He just lets the field go off to infinity rather unphysically. So what we really want to do is see what kind of...
Is that just a reflection in the middle of that?
Yes, it's just right here. Yeah, it's just a reflection from the light source. So yeah, so what we're really looking at is what kind of effect you get when you actually put this top plate on, because obviously experimentally you have to have a top plate. You can't just have an infinite electric field. So today I've got a layer which is even worse, it's inviscid. So we're in a very special liquid crystal limit here. An inviscid perfect dielectric held between two horizontal electrodes. Bottom plate I'm going to fix at 0 voltage, and then I'm going to put the top one at some fixed non-zero voltage. So non-dimensional governing equations. I'm inviscid, so I'm going to recast everything in terms of a fluid potential, and using Maxwell's equations I'm going to recast the electric field problem in terms of an electric potential V, and I will switch constantly between calling it an electric potential and a voltage. So in my mind it's the same thing. So in the fluid region I'm going to need to solve Laplace's equation for the fluid potential and for the electric potential, whereas in the passive air region above I only need to worry about Laplace's equation for the electric potential. Boundary conditions, we've got no penetration through the bottom plate, and again fixing the bottom plate at 0 volts and putting a non-zero voltage on the top plate. And the way I've non-dimensionalized on the layer thickness. So my fluid layer, if it was a flat layer, that's at 1. So my top plate's always going to be bigger than 1, otherwise my top plate would then be below the surface of the fluid. And then all the physics, most of the physics comes in at the interface with these interface conditions. So the top one here, this very long one, is the balance of normal stress at the interface. So I've got to balance the pressure terms from both sides. This nasty looking thing here that stretches onto the next line is Maxwell's stress, and that's then balanced by a curvature term on the right hand side. I have a kinematic condition, continuity of the normal displacement field, continuity of the electric potential across the interface, and then along with that comes continuity of the tangential electric field. So these are all just Maxwell's conditions at the interface. And within there, I've got 3 non-dimensional parameters. So I've got 3 handles that we can turn in this problem. I have an electric Weber number, which I'm just going to think of as being proportional to the applied voltage squared. An inverse bond number, which is proportional to the surface tension, and the ratio of the permittivities in the 2 layers. And then also, experimentally, you can also control the initial fluid depth and the initial cell electrode spacing as well. So that's H and D. So anytime you see a variable with a hat on it, they're all dimensional parameters. Anything without a hat is dimensionless, I should point out. So it kind of proceeds in a very normal mathematical way with a linear stability analysis. Linearize about a steady, unperturbed state and seek Fourier mode solutions. And eventually, after some tedious algebra, we get down to this dispersion relation. Where this first term here is just the dispersion relation for gravity capillary waves, and then that's modified by this electric term. And this term here is always positive, so with the negative sign there, the electric field always destabilizes the layer. The moment you put an electric potential or an electric field across the layer, it destabilizes. I can then set this equal to 0 and solve to find the critical Weber number, so to find the critical applied voltage that I would need to then see an instability. And then at the same time I can solve to see what the critical wave number would be of this instability, so kind of give an idea of what this initial instability will look like. So here I've shown you a couple plots of the dispersion relation for 2 different cell thicknesses. So one with D is 2 on this side, so that means that my electrode spacing is twice the thickness of my fluid layer. And one for D is 5, so my electrode spacing is 5 times that of the initial fluid layer. So what I've plotted here is the wave speed, c squared, which is just the dispersion relation divided by the wave number squared. And you see the behaviour in both of them is very different. So I've plotted it for different values of the Weber number over d squared. That just means that for each layer, regardless of whether it's that thick or that thick, for each value of Weber over d squared, I have the same electric field going across the layer. So here, for d is 2, you can see that the most unstable mode is a long wave mode with 0 critical wave number. But as I increase the layer depth, my most unstable mode will come in with a order 1 wave number. So we wanted to look at this in a little bit more detail. So I looked at the nature of this minimum as it approached the long wavelength limit. And I can then write down an expression for the second derivative of this. And obviously my stationary point will change sign from maximum to minimum as this changes sign from positive to negative. And quite nicely, I can get analytical solutions for the 3 roots of this expression. So each of these... Yes. So each of these is a critical thickness. So when my cell spacing reaches that critical thickness, I'm going to transition from having an instability with a 0 wave number to an instability with a non-zero critical wave number. I can instantly throw out the bottom one because it's always less than 1. And then the other 2 I can then plot. So I've got this phase diagram here. So what I've done is I've plotted the roots DC1 and DC2. So DC1 is most of the line that you can see, and then the second root's just this little hump at the bottom of each curve. And so what I've done is I've plotted this for various values of TOS over various surface tensions, and for 3 values of the ratio of permittivities. So for 1 close to 0, 1 close to 1, and 1 that's 30, which is the experimental value for propylene glycol. The dashed line here is the limit of that first root as my ratio of permittivities tends to infinity. So really 30 here is large enough to be considered infinite. Anything it lies pretty much right on that curve. So anywhere below these curves, my instability will come in with a 0 wave number. So I think of that as when the layer goes unstable, it would just look like the whole layer just moves up on it in a hole. Whereas when it's non-zero, that's when you'll see wrinkles in the layer. So I've called this this is your wrinkling regime, and this is your non-wrinkling regime. The really interesting bit is down here in this tiny little corner. So what's happening here is if you slowly decrease your cell spacing, you'll start off with an instability that will come in as wrinkles. You'll lower it down further, and you'll enter a regime where you get no wrinkling. And then as you still reduce your cell gap further, the wrinkling instability is going to reappear right down here at the very bottom. And that's something that the experimental physicists are looking at to see if they do see any evidence of this experimentally, bearing in mind that this is just a linear stability analysis. The other thing I've looked at is a long wave analysis to look at the nonlinear evolution of our fluid layer. So here we've got 2 different aspect ratios that we can consider. So we've got one for the fluid layer thickness and one for the cell spacing thickness. So I'm always going to assume that my fluid layer is a thin film. And then I've got 5 possible cases for how far away this top plate is from the fluid layer. It turns out, so initially I can automatically throw away case number 5 because then my top plate will lie below the surface of my fluid layer, so that's unphysical and non-interesting. The first 3 are very boring cases. It turns out in all 3 of these cases that your thin film is so thin that most of the electric field is in the air gap above. So essentially your thin film doesn't feel the effects of the electric field, it's all happening in the air above. But the interesting case is here when D is ordered delta, so when both layers are of the same order in height. So both regions are thin films. I can solve my whole set of governing equations and come down to two leading order evolution equations for the surface. So here H naught is the leading order part of the surface layer height, and where phi naught is the leading order part of the fluid potential. And so in the plot I'm going to show you what I've done is I've solved these numerically using COMSOL, which is a finite element numerical solver. And I've solved subject to these boundary conditions. So instead of being a layer, I've pinned the contact lines at either end at 0. So instead of a fluid layer, I've now got a very elongated, flattened drop. And d phi by dx is 0 at either side, so I've got no fluid flow in or out. And what happens is this. So the black or the dark blue line that you can probably just about see there is the profile when I've got it's a steady profile when there's no electric field present. And then as you slowly increase the electric field, the drop then shrinks in at the sides and expands at the top, very much like the numerical experiments, or the actual experiments even, that I showed you right at the very start. All of these are stable, steady solutions. And again, this qualitative agreement, so I've done this with the parameters here, the epsilon p and the tau, that are the same values that you would use for a propylene glycol that's about 150 microns thick. The only discrepancy I've got just now is that my linear analysis predicts that that this system should become unstable with a voltage of about 187 volts, whereas here, this top curve that I've shown you is for a voltage of 300 volts, and I still get a stable profile. The only explanation I've got for this at the moment is because my linear stability analysis was for a semi-infinite film, whereas here I've constrained it by pinning it at either end, and that's probably the discrepancy between the two. So just to kind of finish off, so I've shown you a linear stability analysis, and we've seen that the critical wave number changes from being a long wave 0 most unstable mode to an order 1 most unstable mode. And we've got this evidence of this funny re-emergence zone for very small layer depths and for very small surface tensions. I'm currently working on the nonlinear analysis and doing a thorough exploration of parameter space to see if I can find any regions where I do see static wrinkles, and also to try and see just if anything else interesting happens with different boundary conditions, considering thin layers as well as drops. And I did promise that liquid crystals would feature somewhere. The aim is to extend this, to do this with a nematic liquid crystal, and to see how the influence of having the director field in there aligning with the electric field, how that would then distort the drop shapes that you would see. So yeah, thank you very much for your attention, and I'll be happy to take any questions.
I wish to invite questions now.
Why it's only one-dimensional? Why no any instability in two-dimensional? Might be more soft instability in two-dimensional.
Yes, there might be. They were also planning on a...
Especially for finite cube instability.
I'm going to expand this and make it a axisymmetric, so that when I'm considering a drop, it would then be axisymmetric, and see if I get then different instabilities, because of course the drop doesn't need to remain circular.
How do you model the fact that the amount of material is fixed? Is there, so you need think of the case of a drop. As you increase the voltage, the drop changes its shape, but it doesn't change its volume.
No, it doesn't.
Is that in the model?
Yes. So back here with this kinematic condition, this is also my mass conservation. So at either side, I've pinned the contact lines, and I've got no flow in and out. So if I integrate this up across the layer, it then does give me the integral of h naught across the layer. It doesn't change in time. It does conserve mass.
And if you look at the steady state problem, do you have to impose that as a condition? If you look at steady state problems, How then do you impose the condition of constant volume? Because you have to compare like with like.
Yes. Well, the model that I'm using, it does conserve volume. I have checked it thoroughly that it conserves volume.
Yeah, that's the time-dependent problem, but the time-independent problem.
The time
You have to
independent.
describe the volume, don't you?
The time independent problem, I can solve it with a constraint.
Oh, okay.
I solve it with a
Yeah, okay.
constraint. There's an extra term in here that kind of gets hidden and absorbed into other terms that then does constrain the volume.
Tom?
So what modifications do you expect if you add the viscosity of the fluid?
I think adding the viscosity, I don't think it will qualitatively change the behaviour. I think it will only affect the timescales over which.
You don't think it will change the critical weight number?
I think it might. I don't know. I've not really thought of it in too much depth. No, it will definitely change the timescales because increasing the viscosity is also going to want to damp down any instability.
You know, the parameterization that you use, once the thing forms a capillary bridge, it's not a single valued function anymore. So
Yeah, and
essentially, you're just, you want to explore the onset of instability.
Yes, yes. The thin film model is not going to work for when it forms a capillary bridge.
The other thing is, what about surface tension? Have you, because once you have a curvature, then you've got to have the Laplace pressure balancing the at the interface. Does that make a difference? Does the surface tension play a role?
Yes. Yes.
So, where have you?
So surface tension comes in this top term. So that's my inverse bond number, which is proportional to the surface
Sure.
tension.
Any further questions? Well, apparently there's none. Thank you very much for your